Welcome back, and we're going to continue our journey through textures of magmatic sulfide deposits and what they tell us about the origin of ore deposits. And so in the first section we talked a lot about disseminated ores. We talked about physical properties of sulfide liquids and the way that allows sulfides to essentially attack the rocks that they're sitting in. And a lot of the features that we see in the rock are the result of the interaction between hot sulfide liquid that's moving around within partially molten or sometimes completely solid host rocks and country rocks. So we're going to continue this now, and the next stage of this little journey is to look at a variety of textures which are commonly referred to as breccia ores, and we'll see that indeed some of these really are truly breccias. Some of them are a little bit more interesting than that, and we'll consider about how we might set about interpreting these textures and what they tell us. And we'll conclude with a bit of a journey through the remarkable Nova ore body in Western Australia, which is fascinating in that it actually contains examples of a great many of these different kinds of features that we've been talking about and describing. So the rocks I'm going to be talking about now for the next little while are what we call sulfide matrix breccias. What's a sulfide matrix breccia? Well, it's an aggregate of silicate fragments, rock fragments, molten or partially molten silicate, disaggregated grains, sitting in a matrix of now solidified sulfide melt. And as we'll see, these come in quite a variety of different shapes and sizes, but I'm going to pick a couple of examples which really exemplify some of the real sort of typical features that we see in many of these ore breccias. So a couple of things I want to get out of the way first. So some of the breccias that we see are really genuinely breccias in the sense that they are fragments of rock incorporated in another rock as a result of purely tectonic processes. So we'll call these things tectonic breccias. They've often got this horrible German name, Durchbewegung, which means cutting through. Up until we started doing this work, everybody had pretty much concluded that almost all magmatic sulfide breccias were variations of this, and that they were essentially all tectonic, and that they were the result of just mechanical incorporation of rock fragments into sulfides during deformation. And in some cases that is certainly true, and here's a very good example of one. This is from the Emulsion ore deposit, which is in Western Australia. It's a komatiite hosted ore body, except there's no komatiite inside. This is sulfide originally derived from komatiite flows, which is now sitting in a shear zone out several hundred meters away from the nearest komatiite, within very, very intensely deformed and myelonitized country rocks. These are actually dacite schists, or dacite gneisses almost. And these are fragments of that country rock caught up within the sulfide. Everything's massively foliated. The sulfides themselves are foliated. The clasts are folded and scrunched, as you can see here. So there's really no doubt this is a highly deformed rock, and what you're looking at here is a tectonic breccia. So, as you go along, you'll see that a lot of the features that we're seeing in our magmatic sulfide breccias are actually much more delicate than this, and couldn't possibly have survived the kind of deformation that produced these features. Now we've already come across these things, so these are some nice examples of emulsion textured ores, and again these have often been thrown in the category of breccias, but as we've seen, they're not. These are not fragments of rock at all. These are actually mixtures of two immiscible liquids that have solidified together. And here are some examples that we've already seen from Silver Swan, komatiite, Western Australia. These are some of the emulsion textured ores from Norilsk. That's from one of the ore deposits in the Tectonic part of the district. These things were actually first identified at Sudbury, and this is a very famous sample. This is a sample of what is known by or used to be known, maybe still is, by the miners at Sudbury as sheep shit ore. And these are little fragments of molten silicate floating around in sulfide. And this material was actually first identified back in the early 1960s by Hawley, who was one of the early pioneers of really understanding Sudbury geology. And he was the first to recognize that these things were actually mixtures of liquids, and that these textures were actually an important part of the growing body of evidence that said that these magmatic sulfide ores were actually magmatic in origin, which was back in the sort of 1950s and early 1960s, was a very much live debate. So this is a very historically important texture in our development of the understanding of these types of ores. So these things are not breccias in any sort of normal sense of the way we use the term. They're liquid mixtures, they're emulsion textured ores. Now when we're talking about sulfide matrix breccias, from which I'm excluding these previous two categories, I'm excluding the tectonic ones and excluding the emulsions, then there's a few different models, really mainly models related to dynamic emplacement processes versus models related to passive injection of sulfide to explain these things. One of these, and this is one which I've actually liked myself for a long time before I started changing my mind about it, is that perhaps some of these sulfide matrix breccias are actually the result of gravity emplacement, gravity flows of sulfide melt within trained silicate clasts. These things potentially being emplaced downward in sill dike networks during stages of a magmatic event where the magma is actually flowing back downward into the conduit again. And that this could potentially give rise to some of these spectacular kind of features. Now, one place where that probably is true is the formation of breccias in the Sudbury offset dikes. Now, you might have heard a little bit about these in other lectures, but basically the Sudbury offset dikes are the result of downward emplacement of slurries of silicate, sulfide, and silicate rock fragments into deep gashes and fractures which are generated in the floor of the Sudbury impact melt sheet. But this is a very particular, very sort of specific occurrence, which happens as a result of the fact that Sudbury represents a gigantic impact event. But we do see some of the features which are quite characteristic of the Sudbury offset dikes in other deposits as well, which didn't form that way. So I've already, in sort of the previous sort of part of this lecture, we already talked about the formation of infiltration melting fronts, and I talked about generation of some of these breccia zones underneath sulfide ores at Kambalda, which are the result of sulfide percolating into fractures in the underlying footwall rocks. Now, some of the features that you see in these rocks look remarkably similar to some of the features that you see in these, but I'll try and as we go along, I'll try and point out some of the ways we might be able to tell the difference. So, and the example I'm going to give some of the best and most important examples of sulfide matrix ore breccias from this deposit. This is the Voisey's Bay deposit, which is in northeastern Canada, in Labrador. It's a proterozoic age deposit, and it's a deposit which formed in a network of sills and dikes, which was probably connecting a whole series of intrusions, feeding magmatism higher up in the crust. And one of the characteristics of Voisey's Bay is that a lot of the ore bodies are hosted not in horizontal intrusions, but they're actually hosted in vertical intrusions, or they're hosted in places where the vertical intrusions actually became horizontal or fed into larger sill-like bodies. And the biggest ore body at Voisey's Bay, the most important, is this thing called the ovoid, which is a huge, hundreds of meters wide and thick body of almost pure massive sulfide, which sits at a point where a quite narrow dike rolls over, turns horizontal, and then flares out into a sort of trumpet-shaped or sort of basin-shaped accumulation of sulfide. What's on top of it, we don't know, because the top of it's eroded off. But it looks like it might be the entry point into some sort of sill-like intrusion. Anyway, whatever it is, if we look at the rocks which sit around the main massive sulfide ore body, they all look like this. And these are classic examples of sulfide matrix ore breccias. So typically the rocks are anywhere from about 10 to about 50% sulfide, and they're full of rock fragments. So the interesting question is, well, what are these rock fragments and where do they come from, and what does that tell us about the origin of the ores? So here's a beautiful example. This was actually given to me by Steve Beresford. And subsequently, a whole lot more samples came from Peter Lightfoot, who's probably the global expert on this ore deposit. So what I'm going to show you here is a whole series of XRF maps. You remember that technique that I introduced in the last lecture, where basically we measure the concentrations of a whole lot of different elements at quite high resolution on a cut surface of the rock using X-ray fluorescence. So we build up element maps of these rock types. And here's a beautiful example from this sample. This turns out to be a really interesting sample. So there's not just one rock type in this breccia. It turns out there's actually several. And the most important ones are this one here, which I've labeled peridotite. That's actually a fragment of ultramafic rock. And it's really interesting because there are very few ultramafic rocks at Voisey's Bay. About the only place you find them is actually as fragments in these ore breccias. And this is basically an olivine cumulate. It's green there is olivine, and the blue there is plagioclase. So these sort of rounded fragments of this sort of material, you can see that there's actually 3 or 4 of them stacked up together. And then we've got a couple of other interesting rock types as well. This one up here, that's a northocite. That's an almost pure plagioclase rock, and it's an almost pure anorthite plagioclase, very unusual composition. And this thing here is a hercynite hornfels. And this is a rock which is made of calcic plagioclase, hercynite, which is basically a pure iron spinel, iron aluminium spinel. And this rock's also originally had in it a lot of corundum, which has since been replaced by hercynite. So now that's a very unusual mineral assemblage, and what that tells you is that this is the residue of a piece of country rock which has been partially melted and had most of the melt taken away from it, and all that's left behind is this really refractory material, very, very high temperature material, which just simply couldn't be melted any longer. So effectively these things are like furnace bricks, and these were either being carried around in the sulfide or they were being carried around in a silicate melt. Which was then displaced by sulfide. So let's have a look at how these textures actually play out. Now the other interesting thing about that is these things here, these little black grains, which are sitting out in the sulfide. And if we look at those close up, here's an enlargement of the XRF map of that sample. What we see is that these things are actually plagioclase crystals. They appear black in the hand sample. Very confusing when you first look at it. You'd never think they were plagioclase, but they are. They're plagioclase full of lots of little fine dusty inclusions. And they appear to be growing outward from the breccia fragments, particularly from these hercynite hornfels fragments. So a lot of these have got little clouds of plagioclase crystals extending out around them, and then what appears to be happening is they appear to be growing out into the sulfide. Now that really doesn't make any sense. I mean, you can't dissolve any of the components that you need to make plagioclase in sulfide. So, right away we've got a big problem here. So how do we actually explain these sulfides, these plagioclase inclusions in the sulfide? So let's take a look at pull apart another one of these fragments now. And so here's the rock as it appears in normal light. Here's the XRF image. And the components here will just blow a little piece of that up. So you can see what these components are. So we're just going to blow up this little fragment here. And what we see is that, so the yellow material here is all sulfide. That's pyrrhotite and pentlandite. The light blue material here is clinopyroxene. And these are big single crystals of clinopyroxene. That's one single crystal that contains hundreds or thousands of grains of plagioclase. And also contains crystals of olivine, which is the light green material here. All of this light green stuff here is olivine. So these big crystals that enclose lots of smaller crystals of another igneous phase, these are called oikocrysts. These are clinopyroxene oikocrysts. And another thing to note is that when you look at these closely, there's no sulfide in them. There's a little sulfide vein that cuts it, but there are no sulfide inclusions within that clinopyroxene oikocryst. So that's another puzzle. So we've got to explain those. We've got to explain these plagioclase crystals, which seem to be floating out in the sulfide, although they can't possibly have grown there, and the general sort of overall mineralogy of the rock. So now these things here are xenoliths. These are hornfels xenoliths. Big fragments of them, quite foliated. That foliation is probably inherited from the original country rock. The country rock are very strongly foliated gneisses. So now let's pull this apart a little bit more and just take a look at sort of the 2D structure of what it's made of. So in this image, I'm just pulling out everything except the plagioclase. So there's the plagioclase framework. There's the sulfide. And what you notice is that the plagioclase framework in the silicate and the plagioclase framework in the sulfide actually look very similar. very similar kind of textures. So what that tells you is that this plagioclase framework is actually early, and it predates the presence of sulfide in the rock. This very delicate texture tells you that it can't have formed by flowage of some sort of slurry or crystal mush, because you've got these beautifully delicate interconnected 3D framework of plagioclase grains. So what must have happened is the sulfide liquid must have actually percolated through this plagioclase framework, pushing out the low melting multiphase silicate component. So that should now, in the light of the previous, some of the stuff I showed you previously, this should sort of ring some bells. So this is very similar to the kind of process which made our spinifex ore. It's very similar to the kind of process which makes matrix ores. It's sulfide pushing out and displacing a silicate melt component that's originally sitting within a silicate crystal framework. So that's what's happening here. The sulfide melt is pushing out a lot of this material, but it's leaving behind this refractory plagioclase olivine component. Now here's another line of evidence. So this is now another 3D CAT scan image, and this is a CAT scan image of a Voisey's Bay breccia sample. This is only there's only about 5% sulfide in this rock. It's a bit deceptive because you're looking through a volume of rock, so it looks as if there's much more than there is. But the different colors here represent interconnected sulfide framework. So all of that yellow sulfide is connected to all of the rest of the other yellow sulfide. So what that's telling you is this sulfide is forming a 3D framework through the rock in exactly the same way that we saw in our net textured ores when we were talking about komatiites earlier. So how do we think they formed? Well, this is a little sort of cartoon sequence suggesting how we think it might have happened. That I think what's happening here is that the original rock here was actually a pure silicate breccia. So it was a silicate breccia which was made up of fragments of country rock hornfels and fragments of host rock peridotite. So fragments of olivine cumulates which are derived from somewhere else within the magmatic network. Now we don't actually see any of those preserved anymore. So I'm suggesting that maybe they actually formed higher up in the original network and then kind of got carried down as a slurry during a sort of low energy part of the eruptive sequence. But anyway, however they got there, what we have now is a mixture of rock fragments and silicate melt, which is shown in the yellowish color there. So the next thing that happens is that silicate melt starts to crystallize, and it starts to crystallize plagioclase and olivine, the plagioclase in blue, the olivine in green, and a lot of that plagioclase nucleates and grows around the edge of the rock fragments, and particularly around the edge of those hercynite gneiss fragments, because they're already pretty largely made of plagioclase to begin with, so there's plenty of places for the plagioclase to get a hold and continue to grow out into the silicate melt. So now the temperature drops a little bit more. Now we start to grow another phase, and now we start to grow these clinopyroxene oikocrysts. So here's the clinopyroxene starting to grow from the silicate melt, enclosing these plagioclase crystals and some of the olivine. Now at this point, we now flush the whole thing out with sulfide. So this is now an injection of sulfide that's coming in from above, probably again flowing down a 3D sill dike network. Remember, the sulfide liquid is very dense, it's very runny, so it's, at magmatic temperatures it's very highly mobile. And it's going to have a very strong tendency to flow downhill. So in this case, it's flowing down into this silicate rock breccia. Now, why is that happening here? Well, if you recall, I showed you that where a lot of the ores sit at Voisey's Bay are sort of kind of at pinch points in the magmatic system. There are places where dikes are feeding into subhorizontal sill type intrusions. So these are really good places where you're likely to be accumulating lots of xenolithic fragments, kind of choking the entrance to the sills. So that's why they're there. But now the sulfide comes in and starts pushing out the remaining silicate melt. Now as it does that, it's going to leave behind, push the melt out of the way, but leave behind all of the previously crystallized silicates. So now this plagioclase framework is attached to these fragments, so it's fairly strong. It stays put. And the sulfide just then simply pushes everything else out of the way, and you end up with the texture that we see down here on the bottom right, and the one we've been talking about. So that's how we think the Voisey's Bay ore breccias form, and And also, I think that's a pretty good model for probably how most of these kinds of sulfide matrix ore breccias form. They've all got their own particular sort of quirks, and they've all got their own mineralogy and rock type fragment assemblages and so on. But a lot of them have these same sorts of characteristics. In other words, the sulfide matrix breccias are actually part of the same story. They're all related to this same kind of story about sulfide melts being highly mobile, highly corrosive, and able to do a lot of damage to their immediate country rocks. So putting all of that together, this is a little cartoon from a paper I wrote about 4 or 5 years ago now, attempting to sort of integrate a whole lot of the things that we knew about magmatic nickel sulfide deposits, particularly in mafic intrusive settings like Voisey's Bay and many of the others. This is how we think that a lot of these different kind of sulfide textures might actually relate to this sort of very stylized kind of geometry. So some of our sulfide globule ores, these are basically just frozen in sulfide droplets. We might find these in the margins of the intrusions or in some of the cumulates. The matrix textured ores, we find those where we've got sulfide percolating down through pre-existing silicate cumulates, usually olivine, although they don't have to be. Sulfide ore pools getting trapped in sort of blind alley offshoot intrusions. This is now what we think that some of the Norilsk intrusions might be. Sulfides accumulating at the basal contact and forming infiltration melting fronts, melting down into the floor. This is a beautiful example of one of these melt infiltration fronts from a deposit called Eagle in the USA. Sulfide melting the shale, just like we saw at Norilsk. Here's a Voisey Bay style type of thing with sulfide invading a pre-existing silicate intrusion breccia. And then we also get these kinds of features. These are basically sulfide vein stockworks where the sulfide's invading fractures in the country rock and in some cases melting them and corroding them as it does so. And we'll see more of this in a minute. And then these kinds of sort of unusual Sudbury type globular ores with these very kind of irregular variable composition sulfide globules, which we think might represent ripped up massive sulfide that's originally solidified somewhere else in the system and then been picked up and transported around. So putting all of these things into a sort of spatial story lets us start to put together some key evidence for ore forming processes, and also potentially if we're out exploring for these kinds of things and we start to intersect some of these kinds of features like these globular sulfide ores, these are likely to make a halo which is much bigger than the actual ore body. Then understanding these textures helps us to know how to explore and navigate around a potential mineral system. So I just want to say a little bit more about how we think some of these ore breccias might form, and particularly how. So essentially, what I'm arguing is that the sulfide matrix ore breccias start out as predominantly silicate matrix breccias, and then they get invaded by sulfide. Well, why would that happen, and what sort of circumstances would that happen in? Well, this is a very sort of simplified diagram showing the sorts of geometries of different types of intrusions, mafic and ultramafic intrusions, that we find nickel sulfide deposits in. You'll recognize the one down the bottom right there. These are the Norilsk chonolith type intrusions, these horizontal sort of tube-shaped sills. But the one I want to focus on now, because I think these are the ones that actually really give us a clue to what's going on. There are quite a number of deposits, and more that we're recognizing now, which are actually forming in things that we call blade-shaped dikes, or in things like sort of elongate funnels or flared dikes, which are basically sort of dike-like bodies that open up into tubes or sort of wine glass type geometries. I think that these things are actually quite closely related, and there's actually a complete transition between them in some deposits. But I just want to focus on these ones for now. And I'll pick one particular example that we've been working on a fair bit over the last few years. This is the Savannah deposit, formerly known as Sally Malay. The older papers on it call it Sally Malay. This is up in the Kimberley in Western Australia. It's a Proterozoic age, about 1800 million year old body. And it turns out it's actually one of these bladed dike type bodies. So this is what it looks like now in 3D. That's the surface expression of it, which is this sort of kind of elongate pear-shaped thing with ultramafic cumulates at the bottom, mafic cumulates at the top. It's beautifully layered. The layering runs across it but dips vertically. And also the ore body, this is the massive sulfide ore body sitting on the basal contact, that also dips vertically. So we think what the original geometry was up on the top right here, that it was basically a sort of slightly flared out dike with a bottom edge. Now, this comes as a bit of a surprise to people because people tend to think of dikes as being things that just kind of go forever and basically sort of go all the way down to the center of the earth. But in fact, most dikes don't. If you look at dikes side on, most of them are actually more or less sort of circular in shape. Many dikes actually have bottom edges. Most of the propagation of dikes actually happens not purely upwards, but a lot of the propagation of dikes is sideways as well. So as cracks open and fill with magma, they typically actually start forming at fairly shallow levels where the crust is more brittle, and then the fracture propagates laterally and downwards as well as upwards. So dikes have bottom edges, and in this particular case, that's what we think savanna is. Now, the interesting thing at savanna, and in fact in most of these deposits that are hosted in these types of intrusions, the bottom edges of them, the ore bodies, look like this. They're sulfide matrix breccias. Savanna is a very spectacular example. It's full of and the fragments are a mixture of country rock. The country rocks are garnet-bearing gneisses, so you get these really spectacular garnet-rich sulfide ores. And also a lot of these fragments are actually fragments of the intrusion itself, but they're mostly fragments of the actually chilled margin of the intrusion, which is kind of interesting. We don't find a lot of fragments of cumulates. They're mostly fragments of fine-grained norite, which we think are inherited from the sidewall of the intrusion. But these things have now accumulated at the bottom edge of the savanna dike. Now, also, if you focus on this sort of 3D model here over the left, you notice that projecting off the bottom of the ore body is actually a dike-shaped body of sulfide. And for quite a while, this was interpreted to be some sort of a shear-hosted tectonized sulfide. But in fact, we now know from being able to get a good look at it underground, it's actually not. This is actually a primary sulfide dike. It's got primary margins with emulsion textures around it, and lots of silicate rock fragments in it, which exactly match the ones that we find in the intrusion itself. So this is a downward propagating sulfide dike that's propagating at the bottom edge of the intrusion. So how do we think this forms? Well, this is a little sort of cartoon. Here's an early stage in the development of a bladed dike, but as it expands laterally, it starts to find rocks, country rock layers that are relatively easy to erode and melt. So it starts to inject along those and start to develop a little bit more of a sort of sill or tube type geometry. That's how we think some of these chondroliths form. Now, while that happens, if we're generating sulfides as a result of this sort of thermal erosion and assimilation here, those sulfides then sink down to the bottom of the dike and accumulate at this bottom edge. And this is what we think might be going on at savanna to make these kinds of features. And that explains why we get fragments of country rock, but also we get fragments of the chilled margin of the intrusion. They're being derived from this contact up here. And this feature of having of the sulfides themselves actually extending down as sort of sulfide dikes off the bottom of the intrusion, we find this in quite a few other places. This is an example from the Tutu deposit in the Raglan area in Canada. This is from one of Jim Mangold's papers, the purple and red material here is again sulfide-rich, sulfide matrix breccias forming a dike extending down into country rock, which is a basalt in this particular case. So this raises another interesting idea, and this sort of goes back to something that we saw when we were talking about these Kambalda infiltration melting fronts, that in some cases where the country rocks are a little bit brittle, these melting fronts are forming not just by sulfide melting country rock, but actually by sulfide exploiting original fracture systems in the country rock. We'll see this in Nova in a minute. And as they do that, they're carrying heat in and generating melting. So in this case, you could actually be generating a breccia, which is not, which is basically a monogenetic breccia. It's made entirely of country rock fragments, but it's basically made by fragmentation of this sulfide, intersecting sulfide veins. So really what you have is sort of an intersecting array of sulfide veins that can generate these breccias. But of course what this does is this now carries a lot of heat from the original magma down into the country rocks and starts to melt them. So this might actually be a way by which the intrusion actually propagates. That the intrusion might actually be getting generated in part as a result of the sulfide advancing ahead of it and kind of helping it to force its way into the country rocks. And this is really just sort of a speculative idea at the moment, but if it's right, it's kind of an interesting one, because it says that there could be a feedback involved in formation of some of these kinds of ore deposits, that rather than the sulfides just basically being dumped out in trap sites, the sulfides are, and that's the sort of the standard view, that we think of the sulfide just being carried passively and then just dropped out like heavy minerals in trap sites at the floor of the flow, or the floor of the intrusion. Maybe they're doing a bit more than that. Maybe they're actually digging their own trap sites as a result of this sort of invasion and melting kind of mechanism. So I'll just leave you with that idea. So just some sort of general conclusions before we go and look in a little bit more detail at Nova. So putting together all of the stuff that we've been talking about over the last sort of hour and whatever it is, there's a continuum between infiltration breccias and emulsion textures. They're all basically forming by similar processes. There's also a continuum between matrix ores, there's patchy disseminated ores, spinifex ores, and infiltration breccias. They're all forming by essentially the same process. This sulfide is a hot knife through butter kind of concept. The process is driven by percolation of hot, dense, low viscosity sulfide melt and displacement of low melting silicate component, either at infiltration melting fronts or within crystal mushes within the intrusion. Sulfide matrix ore breccias are forming mostly by low energy gravity driven downward percolation, and not, as some people have speculated in the past, and a lot of people still think, not by high energy volatile driven upward emplacement. These aren't volatile overpressured hydrofracture breccias like you find in porphyry systems. These have a very different kind of origin, and there's that hot knife through butter kind of sulfide concept again to try and cement that. So let's now move to Nova-Bollinger and have a look at how all of these processes come together to make a really interesting and intriguing ore body. So we are here. We're in AFO's the Albany-Fraser origin. It's in it's a Proterozoic orogenic belt forming the southeast margin of the West Australian craton, particularly the Yilgarn craton. And this is a long section through the system. So there are two intrusions at Nova which actually come together and merge. The upper intrusion is a classic layered intrusion. It's alternating layers of ultramafic and mafic cumulates, rhyodites and norites. A little bit of sulfide in it, but not very much until you get right down to the bottom. It's got a lower marginal zone, which grades up into the cumulates. And then there's a lower intrusion, and this lower intrusion is composed of primarily ultramafic rocks or sort of transitional ultramafic to mafic rocks, very, very variable plagioclase contents. It's got olivine, a lot of olivine and a lot of orthopyroxene in it, very complicated textures, and has sulfide in it pretty much everywhere. The main massive and semi-massive ore bodies that we're going to be looking at, Nova here and Bollinger here, sit within this lower intrusion and off the bottom of it out into the country rocks. Now, interestingly, where these two intrusions come together is this little zone here called C5, and this is essentially the zone of the lower marginal zone of the upper intrusion with a high concentration of disseminated sulfides. And this seems to be the point where we think the lower intrusion actually budded off the upper one. So now this is a leapfrog model. This is a 3D image now, looking down on top of the lower intrusion with the upper intrusion removed. So the lower intrusion is shown here in this green color. The red and orange colors are massive and semi-massive ores. And as you can see, they extend well beyond the margin of the intrusion. So now that's the top view. So now we're going to take a look, looking along the axis of this intrusion and looking at a section through it. So we are looking along the axis of the lower intrusion. And this is what it looks like. It's a sort of lozenge-shaped body of ultramafic rocks with lots of disseminated and massive matrix sulfides in the lower part. And here are the massive and breccia ores extending off to the side of it. The system has been deformed, and part of this displacement of the sulfides away from the intrusion is probably to do with the intrusion being sheared off the top. But as we'll see, a lot of it is also primary magmatic. So let's have a look now. So the next few images will be based on this very sort of stylized image of a cross section through the lower intrusion. So the lower intrusion is in these purpley colours, the sulfides are in these orange colours, the yellow and green represent the country rocks. So the green is a mafic granulite. This is basically an amphibolite, very, very dense, massive, largely unfoliated mafic granulite rock. These green and yellow things here, this is a garnet pyroxene paranite, and so these are derived from metasediments, but they're made from metasediments with quite mafic compositions. They contain lots of garnet, and they contain lots of interlayers of what's essentially amphibolite, or it would be amphibolite, except it's at higher metamorphic grade. So it's actually now mostly plagioclase pyroxene, alternating with quartz garnet pyroxene paranites. So now within the intrusions, we see a lot of what are basically just absolutely typical, beautifully preserved neck textured ores. And here's a lovely example. So this is a polished section. The grey material here is all olivine, and the lighter coloured material is sulfide, and the sulfide forms this beautiful network that's completely interconnected and completely encloses all of the olivine grains. So this is classic matrix ore. This is sulfide migrating through an olivine orthocumulate crystal mush. And this is you've actually seen this image before. This is an XRF image of a slightly lower grade, heavily disseminated or patchy disseminated sample. And in this case, the red here is sulfide. The black is olivine, and the blue and green are two different pyroxenes and plagioclase. There's a lot of complicated mineral reactions going on here that I won't bother you with, but basically what you can see, what I pointed out earlier, you have domains of pure sulfide, just enclosing olivine and nothing much else, and then you have domains where there's no sulfide at all, and the olivines are separated by minerals, which we think pretty largely crystallized from the silicate liquid in between them. So this is a classic case of sulfide forming these percolating pathways through an olivine crystal. Okay, so far so good, but there's nothing particularly exciting about that. But now let's have a look at some of the semi-massive ores sitting underneath the ore body. And I'll focus on a couple of these in particular, but it's just sort of a general introduction to the types. So the first type we get are these so-called hard-walled vein breccias, and this is sulfide invading the mafic granulite. And what we get here is just basically a whole series of intersecting vein sets, and that gives rise to lots of what look like breccias, but in fact they're just basically sort of the walls of the veins breaking up and falling into the veins. Now in some cases these have actually also been sheared and deformed, and these rocks were very hot at the time they were deformed. So a point that I ought to have made is that on a whole variety of lines of evidence, we're pretty sure that this intrusion was placed into the lower crust, and the rocks were at granulite facies when it happened. So these rocks were already really hot when the intrusion came in. So now we get these sulfide vein breccias with these so-called leucosome veins associated with them. We'll talk about those in detail in a second. Some more sulfide veins. This is sulfide cutting across country rock. These sort of carrot-shaped veins, which very often have garnet-rich rims, a mystery which still really haven't solved. And then a variety of sulfide matrix breccias. And in many of these breccias, the country rock fragments are spectacularly contorted. So what's happening is they've been really sort of soft and gooey when they're incorporated into the sulfide, and as they start to get pushed around a little bit, and as they get deformed, they form these really peculiar sort of rootless kind of refolded folds within the sulfide. And then we also get what we call sulfide infiltration ores, where the sulfide's completely soaking in to the gneisses. So let's have a look at these in a little bit more detail. This is a beautiful example of a contact between a sulfide infiltration zone here, and then here's a sulfide vein heading off down into these granulite facies metasediments, and going off the edge of the vein you would get again the sulfide veins, but these are actually now following the foliation in the gneisses and injecting their way along, and they seem to be picking out the layers which are most easy to melt. So they're picking out the layers that are the most sort of peelite-like, and typically these are quite garnet-rich layers. So the sulfide loves to inject along these. These layers here are much more refractory. These are the pyroxene-rich rocks that are much harder to melt, and the sulfide The sulfide tends to avoid those. Then here's an interface between, at the top here, this is just a sulfide breccia with lots of rock fragments in it. And what's happening within this sulfide breccia, you'll see in a bit more detail in a minute, these rock fragments, these are mostly garnet gneiss, and they're breaking up and disaggregating just into clouds of crystals, typically garnets and pyroxene. And those are forming what looks essentially like matrix ore, except instead of it being olivine in a cloud in a sea of sulfide, it's garnet and pyroxene in a sea of sulfide. It's forming these sort of crystal-rich kind of mushy zones. But then down at the bottom of that, you can see here's the garnet-rich paragneiss. These reddish things here are the garnet-rich bands. These whiter things here are magmatite bands. So these are little zones of the rock where the rock's melting and producing a granitic partial melt that's forming these magmatite type layers. Here and then here's the sulfide, which is invading along these partially melted layers and causing the country rock to break up and float up into the sulfide, just like we saw in some of those komatiite examples that I showed you earlier. This is a classic example of an infiltration melting front. The difference being that at Nova, it's tens of meters wide. So now let's have a look at some of these spectacular breccias that I mentioned earlier. This is one of these beautifully contorted soft-walled breccias, and you can see that the way the rock fragments behave in the sulfide matrix depends on the lithology. So these things here are the remnants of what was probably a metapelite. So this was probably relatively easily melted, and where the sulfides are where the most easily melted layers were. But then these are layers of the much more massive pyroxene-rich. Pyroxene plagioclase rock, which is much harder to melt. So that tends to form these much sort of harder walled fragments that just basically kind of float around in the sea of sulfide. Whereas these things are basically just kind of getting crumpled and folded, just sort of like jellyfish within a matrix of this super hot and fluid sulfide. This is an XRF map to show one of these things. In this particular image, the garnet shows up in this version in these orange colors. The black is quartz, and the green is sulfide. So you can see that the sulfide is completely invading the layers with these folded layers. And the folding is probably happening while the sulfide is actually being injected. And then the final example of that is we see these infiltration zones. So this is now a rock which is, you can still see the original gneissic foliation in it, but all that's left of the gneiss are just these pyroxene rich layers, and the sulfide is just completely infiltrated all of the other layers and just formed this beautiful sort of banded sulfide pyroxene garnet gneiss. Really extraordinary, spectacular rocks. And here's another example of that same thing happening. This is this infiltration sort of almost replacement ore, although it's a magmatic replacement, not a hydrothermal one. But here's a really interesting thing. So along the edges of a lot of these bodies, you find these things. These are basically sort of granitic composition pegmatites. These things are actually partial melts of the country rock. So this is the material that's being displaced by the melting of the gneiss by the sulfide. And we see lots of examples of this. And here's a really beautiful sort of smoking gun example of what's going on. So here's one of these these little partially molten layers in magmatite are called leucosomes. A horrible word to remember, but that's what they're called. So this is partial melt of the gneiss, which is starting to leak out. Here's a sulfide vein, and you can see that material is actually leaking out and starting to travel along the wall of the sulfide veins. So this is the sulfide displacing partially molten silicate. So here's what we think is going on. So stage one, so this is I've taken the upper intrusion away to make things a little bit clearer. This is the lower intrusion at Nova. It's basically sort of a tube full of magma carrying sulfide. The sulfide starts to inject itself into fractures in the country rock. Those fractures are probably actually being generated by the expansion as the silicate melt forces its way in. It's got to create room for itself, so it actually starts to generate expansion cracks in the country rock. Sulfide flows into those cracks. Then we start to get olivine accumulating at the bottom of this body, which is now starting to crystallize inward. That's where we start to get the net textured ores generated. But these massive ores are now melting their way into the country rock. And here's the process we think is happening. Here's sulfide veins filling these expansion cracks in the country rock. Sulfide injecting itself in. It finds these sort of softer layers where it can more easily melt its way in, pushes its way along those particular layers within the gneiss, and displaces out the partially molten leucosome material, the partial melt of the gneisses, and that material then backflows up the side of the veins, that's so. Then where you've got very extensive invasion of the country rock, almost everything is gone apart from the refractory layers, and that's what forms these peculiar kind of soft wall mushy breccias. But along the sides of the veins over here, we get these things kind of going on, where this is sulfide, these are country rock fragments, and this is the country rock partial melt leucosome, which is basically fighting for space in the vein with the sulfides. The leucosome's trying to migrate up, and the sulfide's trying to migrate down. We get these sort of mixed zones, these complicated mixed vein arrays developing in the footwall of the ore body. So now these things are very extensive. There's sulfide travels it's a very considerable distance away from the ore body, up to about 30 or 40 meters in some places. What's remarkable about Nova is that we see these textures other places, but they're spectacularly developed over such a huge volume of rock. The reason for this is because the country rocks were already hot when the intrusion came in. So to look at that, let's think about the sort of time scale that these kinds of processes are operating at. So first of all, let's think about the initial setup, which is a sill-like body, the Nova lower intrusion, which is being injected into country rock gneisses, which are already super hot. So they're already at sort of 800, 850 degrees. The metamorphic petrologists tell us that. So this is what the temperature profile through that intrusion looks like. So immediately after the intrusion is in place, you've got this kind of grey line here. You've got a very high thermal gradient at the contacts, but then with time and over a period of sort of a few hundred years, I should have said this red line here in the middle, the red vertical line, that's the temperature at which the intrusion will be entirely solid. That's the solidus of the intrusion. And we get to that temperature after about probably 1,000 years or so. So it doesn't take all that long for the intrusion itself to cool. But it then takes a very long time for the intrusion to cool to much lower than the original country rock temperature. So here we go. So after maybe about 10,000 years, the intrusion's solid, but it's now come down to the temperature of the country rocks. But here's where it gets interesting. So now this is sort of a timeline. So this is temperature here, and this is a time on the x-axis. This is a timeline on a log scale. So this is going day, year, 1,000 years, 10,000 years, million years, 10 million years. So you're seeing. So out here we're looking at basically the history of the entire origin. This is sort of the time scale over which the whole origin starts to cool down. And this here, over the first 1,000 years, this is the time scale over which the intrusion cools down. So this is the temperature in the center of the intrusion here, which starts out probably about 1,200, 1,250 degrees. It takes about 1,000 years to get down to a temperature similar to the country rocks. But here's the thing: this red box here shows you the range over which the sulfide solidifies. Remember, we talked about that a little while back. The sulfide actually solidifies over a melting range between about 1,100 and about 800 degrees, possibly a bit lower. This black line here is the ambient temperature of the country rock. This is sort of the metamorphic grade. So this is the temperature that the intrusion cools to. But when the intrusion is cooled to that temperature, the sulfides are still partially molten. Now, to get below the melting temperature of the sulfide, you've basically got to cool not the intrusion. You've got to cool the entire body of lower crust forming part of this orogenic belt. And we've got a bit of an idea. There's some thermochronology work being done looking at about how long that takes. It's probably the order of around about 10 million years. In other words, these sulfides are liable to be staying molten for anything up to millions of years. So that's why we can get such enormous penetration of the sulfides into the country rock. Now, also while this is going on, we're actually getting compressional deformation happening as part of the development of the orogenic belt, and that pushes some of the sulfides around. and that generates some of the larger scale sort of complicated structural features, which I didn't have time to show you, but they're all operating at the same time that the sulfide is still above its solidus temperature, it's still partially molten. So those features all come together to make Nova the remarkable ore body it is. But the lesson to take away from this is that to understand these kinds of things, you actually have to think in terms of timescales, and you have to think in perhaps some much shorter timescales than we're used to thinking of as geologists. That it's the process of forming an ore body, there are all sorts of different processes that are happening. Some of them are happening at timescales of days, some of them on timescales of years, and some of them on timescales of millions of years. And what we see in the rocks is the end result of the interplay of all of those different processes and all of those different timescales. So that's really the story. So I'll just leave you with this summary, these sort of main messages that you can just as well read for yourself. But basically, sulfide liquids can percolate through silicate rocks once the sulfide content's high enough. Some breccias are actually primary sulfide silicate melt percolation fronts. And I say some because not all of them are. Large-scale breccia ore bodies may actually be extensive percolation melting networks. They're not explosively in place volatile-driven breccia pipes. They're a result of relatively passive, relatively slow injection of sulfide into country rocks. Post-deposition sulfide liquid migration plays a major role in generating ore bodies. It might have a lot to do with why they're there in the first place. And the spatial distribution of textural types can help vector into and assess the potential for high-grade ores when you're exploring these kinds of systems. That's the end of the story, so I'll leave it there. Feel free to contact me, and I will leave it there. So here's how you can contact us if you'd like any more information. If you Google CSIRO magmatic ore deposit research, you'll find our website where we've got a whole lot of other materials, resources, links to publications, some downloadable videos, and including a more sort of extended talk on the Nova deposit. So drop in and have a look, and follow us on Twitter, or feel free to email. So thanks again for listening. Good luck.